Okay, now Antoine, whenever you want.
Okay, thank you. Thank you for inviting me to this very nice seminar. So yeah, today I will talk to you about dynamical supersymmetry breaking in string theory. Okay, so the goal of our research is to find stable non-supersymmetric vacua in string theory. So we will work in the framework of type 2B superstring theory. We will play with D3 branes on non-compact spaces, such that we can take a low energy limit and decouple gravity from the setup. So in this spirit, we will be able to identify all the properties of the vacuum of the string theory to the properties of the vacuum of the gauge theory. So in particular, we will make computation only on the gauge theory side, and it will tell us like if the vacuum is stable or what about the symmetries, the vacuum in string theory. The outcome of this research is to first enrich the catalog of supersymmetry breaking gauge models that you can get from Branes. But also, if we manage to find a suitable large N limit for this gauge model, it will open new perspectives on non-supersymmetric gauge gravity dualities. And finally, something that I will not really comment on during this talk, but deserves to be mentioned, is that all these setups could be used in principle as devices to implement supersymmetry breaking in compactification. So for instance, to echo with the talk that, of Andriana that we just saw, here we could implement supersymmetry breaking without the use of anti-D bonds. So this work is based on a collaboration with Ricardo Agurio, Matteo Bertolini, Sebastian Franco, Eduardo Garcia Valdecasas, Shani Mene, and Baldo Tatice. I put here all the archive numbers for the relevant papers. So first, let me review what I mean when I say dynamical supersymmetry breaking. So you know that in gauge theory, in a supersymmetric vacuum, the energy of the vacuum is equal to 0. This is imposed by the superalgebra. Now, in the case where the supersymmetry is broken by a strongly coupled gauge dynamics, then you expect this energy to scale as some power of lambda, the dynamical scale of the gauge theory. So you see now supersymmetry is broken as a result of the infrared dynamics, and this is what I call dynamical supersymmetry breaking, or DSB for short. So an example of DSB model that I will work with all along the talk is the SU5 model. So it is based on a SU5 gauge group with some chiral superfields, one in the anti-symmetric and one in the anti-fundamental representation of the gauge group. So this model can be checked to be strongly coupled in the infrared, and it has in particular no chiral gauge invariance. So there is no term that can appear in the superpotential. It means that you cannot tune any parameter to make computations reliable. So this model is known to be uncalculable. Nonetheless, different people manage to convince us that this model breaks supersymmetry dynamically with indirect arguments. Some are based on total anomaly matching, some on instant-on computation, and lately on the Witten index. The question is now, how can we find this SU5 model consistently embedded into Branes? So for that, I will describe you with what kind of non-compact geometries we will play with. So in type 2B, we will place the D3 branes at the tip of singular toric Calabi-Yau cone. So we take them to be Calabi-Yau because in the microscopic description in the UV, we want supersymmetry to be preserved. It will only be broken in the infrared. Then we take toric geometries simply because they have a nice set of isometries such that we have like a full set, an incredible set of algorithms that allows us to very easily extract the gauge models from it. I will not review these algorithms, but let me just mention that all the toric Calabi-Yau singularities are classified here as convex polygons in a 2D lattice. So when I will refer to a singularity, I will show you one of these diagrams. And then you should believe me when I will show you the corresponding gauge theory. Then let's look about the branes. As I said, we can have like usually 3 branes. When they are placed at the tip of the Calabi-Yau singularity, they give rise to superconformal gauge theories. So you can break conformality by adding wrapped D5 branes on some non-trivial cycles of the geometry, and they will locate themselves at the singularity because of their tension. where these D5 branes now look effectively like D3 branes, and we will call them fractional D3 branes because they have some fractional charge. Then we will also introduce orientifolds. Orientifolds act as a projection both on the geometry and on the gauge theory. Those ingredients are crucial because they will allow us to get fields, for instance, define the anti-symmetric representation, just what we need for the SU5 model. So let me show you now one example of construction. The singularity represents what is called the pseudo-del pezzo trebi, or whatever. You see that on the toric diagram, you can see that it has a good symmetry reflection with respect to a line to implement an orientifold. We can put on it n regular branes and n fractional branes. The gauge theory that results from the playing with the algorithm is this one. You see 4 gauge groups, and you see that the fractional branes only turn on 2 nodes out of the 4. Now you can play with the parameters. For instance, you can put n equal to 0 and m equal to 1, and you see that it reduces to this SU5 times SU1 gauge theory. The SU1 has no dynamics, it's just a flavor index. So effectively, this is just a SU5 model. Because, and again, believe me, the matter field just turned out to be exactly what we need, an anti-fundamental and an anti-symmetric. This is the SU5 model. The first one was found by Franco and Krefeld, Parkuranga, and Begg in 2027 using exactly this kind of tools. Later, actually 3 years ago, we found with my collaborators like 16 occurrences of this SU5 model in similar geometries, just scanning some of them, the simplest. And so what it shows is that actually the SU5 model is pretty common in this kind of constructions. Once you have all the ingredients that I mentioned, they are not so rare. Now, a legitimate question would be to ask about large embedding of this gauge theory, so that we get closer to what throat, the gravity dual, and all these nice things. So following this idea, Boratti, Garcia, Valdecasas, and Uranga showed that just by adding n regular branes, you can get like a bigger gauge theory, which in principle should be just a generalization of the SU5. So I just took the same gauge group as before, but now there are n regular branes that are present. So n is turned on. If you study this gauge theory, what you can find is that it has in its moduli space 2 flat directions, parameterized by v and v prime. Actually, the operator present in this flat direction are always charged in the only 2 gauge groups for the full gauge theory. So when you turn on one wave, you expect to ease only one part of the gauge group. Let's do so and see what happens. I start with the full gauge group, I turn on both waves, and you see that it eases me down to, again, the twin SU5 model. So this looks promising. But there is an issue that arises. If you perform scale matching, meaning that you link the gauge coupling of the UV and the IR gauge theory here at the scale of the Xing, you can get a relation between the dynamical scales of the gauge group of the IR and with the one of the UV. This relation is shown here, and it depends on the value. Because we fall on the SU5 model in the bottom of the picture, we can relate the energy of the vacuum to the dynamical scale of SU5. Remember that it breaks supersymmetry. And so then, using scale matching, you can relate it to the dynamical scale of the UV theory. But now you see that this term has a dependence in the value. And in particular, you can tune V prime to 0, keeping V finite, to see that the energy relaxes when one of these waves vanishes. This basically shows you that we were on a branch where we could break supersymmetry, but it was right next to a point where supersymmetry was recovered. So indeed, it was not trivial to show that this whole model was breaking supersymmetry, and it's not the case. If you place yourself on the non-supersymmetric vacuum, there is an instability that then drag you into a supersymmetric vacuum. On the geometric side, this instability is related to the fact that the singular space has not an isolated singularity. It has actually a full complex line of singularity. And so when you put your D3 brane on it, it can split into 2 fractional branes, and one set will just escape along this complex line. So it destabilizes the model, and it changes the nature of the vacuum. You can spot this fact that the singularity is non-isolated just looking at the toric diagram. If you see a point between two parallel edges, it means that it's not isolated. If you like PQ webs, 5 Branes webs, you can find it by just considering the dual graph of the toric diagram. And here you see that the segment in blue represents the fractional brane, and indeed it can slide freely vertically on this diagram. This shows the flat direction that I mentioned before. In our later work, 2 years ago, we showed that actually we can build a theorem to say that whenever this feature, this geometrical feature is present, your non-supersymmetric vacuum will be unstable. This apply to all the 16 cases that I mentioned before. So it shows that it's actually quite tricky to embed your supersymmetry breaking model into a large inversion model. But we also saw that now it relies on the geometric property of the singularity. So the question that we ask is it possible to avoid non-isolated singularities? And this led us 2 years ago to a search of to a new scan of toric singularities, especially isolated one, to see if we could find an SU5 model. So we built a list of requirements. The singularity should be isolated, of course, should allow for an orientable projection, should also, the toric diagram should be big enough. I will not explain it, but it's related to the number of fractional branes of different kind that you can get there, just to make sure that we can have like the supersymmetry breaking sector and something else. And finally, of course, the gauge theory that you get should be free of gauge anomalies. We realize that we can impose some constraints on the orientable type. I will skip some details, but this search led us to actually one candidate, maybe the simplest candidate, say, that passed all the tests, and it has the shape of an octagon. You can also see that it has a good orientable projection. So now I will just move on to the gauge theory of this octagon, and we will study it. It is quite complicated. It has 8 gauge groups, and the ranks of the gauge groups are tuned by 2 parameters. Again, n is the number of regular diffree branes, and m is the number of wrapped branes, or that we call fractional branes. It's hard to see what we can get from that, since it's pretty complicated. So let's simplify it a bit. I will remove all the regular branes and keep only one fractional brane. So n equal to 0, m equal to 1. Now you see we just have 4 gauge groups that are turned on. And you can notice that the one in the middle, SU1, is again the sublevel group. There's no dynamics. So we have an SU5, another SU5, and an SU2. If you look at the matter content of the theory, you just recover exactly what you need for the SU5 to be the SU5 model. The SO on this side has no matter charge under it and low energy. So it's just like a super Yannis node. It confines on its own, and it doesn't affect the vacuum energy. So what we just find with the octagon is a double copy of the SU5 model that we name the twin SU5 model. In particular, it breaks supersymmetry as we wanted. Now it do it twice. So now in this model, we can safely add n regular branes, modify the theory. We recover the top of this diagram, the UV theory that is bigger than the one at the bottom. And we convinced ourselves that there should be no instability in this model. Actually, there is something more that we can say, is that the octagon singularity is quite peculiar. It is in fact a generalization of the conic fold that Andriana mentioned just before. What it means on the gauge theory is that the gauge theory, the LG flow will take a special form. It will take the form of a cascading LG flow. What I mean here, to be sure, is that actually the UV theory at the top is connected to the infrared theory at the bottom by an energy flow that effectively decrease the parameter n. And it does so following a sequence of Seiberg dualities. The bottom line is that these two groups, these two models, are not connected only by a removal of diffree branes. There is also a natural energy flow that connects both. And because there is no instability to begin with, we know that this energy flow cannot deviate to a supersymmetric point. So by assumption, we constructed this model so that it has no instability like the one we exposed before. We were also careful enough to check that in the gauge model, there were no other kind of instabilities that would deviate this energy flow. We looked at baryonic directions in the moduli space. We looked at string instanton, and nothing affects the setup. So we really trust this energy flow to have only one endpoint that breaks supersymmetry. So we conclude that the octagon singularity hosts a stable large n embedding of supersymmetry breaking. Now you may say, okay, this is fine, but if you want to find a gravity dual, you should better keep a large parameter from the beginning to the end of the algebra, a large number of colors, to apply the Maltesian limit in the appropriate way. And this is true. So now we will look at building a new energy flow, but with a large parameter on both sides. Let's see what we can get, still playing with the octagon. So this is the result of our work of this year. We, instead of piling up just one fractional brane on the octagon, we decide to pile a number m of it. That would be arbitrary. The gauge theory is more complicated than before, of course. It also creates a superpotential term now with a coupling H. So it is a legitimate question to see, okay, but now does this model again with supersymmetry? And we will see that in details now. First, we restrict ourselves to M odd. We will see why later it is important. If you restrict to M odd, then you can write a composite field, X, in terms of all the UV fields, and all the chiral gauge invariants will be constructed out of trace of power of X. So I have shown a list here below. You see that the list is finite. This is just because the UV fields are finite matrices. You see also that one of these gauge invariant is actually the one that appears in the superpotential. So if you solve the F-term relation, you solve the classical moduli space of the theory, you see that the interaction of the superpotential constrain all these operators to vanish. What you have, the classical moduli space is just a single point where supersymmetry is present. But what about quantum corrections? To solve that, we will treat H in perturbation. So first, put H, the superpotential term, coupling to 0. Now, all the gauge invariants are flat directions. So in particular, you can choose the first one to have a value V and study the nature of the vacuum there. If you do so, you see that V exists the gauge group to something simpler. That is, without surprise, between a super model and an extra node, that is a symplectic group, that is just super Yang-Mills, and again, it confines on its own. So there, the vacuum has a positive energy. You can use the same argument of scale matching to express this vacuum contribution in terms of the UV dynamical scale, and you see that it makes the verb appearing in the denominator. The expression is quite complicated, but all that matters is that you have some profile that seems run away in the verb, because the potential energy relaxes when the verb is infinite. So this seems to be run away and not very good. But don't remember, please, remember that we have to turn on the superpotential. When you add the three-level contribution, you see that now in the potential there are two terms that will basically balance each other, as the graph shows. So what you find is that there is possibility to find a verb that minimizes the energy potential, and there the potential has finite value. So this model again breaks supersymmetry due to the quantum effects. So this is all fine and nice because then we can place M fractional branes in the energy flow before, both in the UV and the IR. And now we have a flow where M is not affected by the sequence of cyberdualities. So we can keep M large on both sides. The solution is stable for the same reason as it was for the model with M equal to 1. And so we find, in principle, a gauge theory that should have a gravity dual. It should exhibit supersymmetry breaking deep in the bulk. And we accept the solution to look like some Roark's road solution that were found for other toric singularities. So this is the main result of the talk, but just now let me say some few words about M even. In this case, the gauge theory is the same. I mean, in its UV description, but what changes is that you can build new chiral gauge invariants. They are some sort of baryonic operators because they are made of some products of fields that are anti-symmetrized with respect to some of the gauge groups. The anti-symmetrization here is shown with the bracket. The point is that those directions are not lifted by the superpotential. So they will generate runaway once quantum corrections are included. And this runaway will not be stopped. So all the backward that you get with m being even would be unstable. You cannot use that to do proper holography. This distinction between m odd and m even is not uncommon in orientable. You can see it in the simplest example. It just expresses the fact that going from even to odd, you change the charges of the orientable. So yeah, it is something that we could have expected. Now, we didn't compute any metric for the gravity dual. We don't even know clearly about the topology of the octagon singularity. In principle, all this can be obtained using the good algorithm of the good toric algorithm, but it's some work in progress. Nonetheless, we can still draw some conclusions just from the lesson we saw in the gauge theory to make some comments. The first point is that on the fractional brane, we had both SU group and SU. The SO group typically arises when you have branes on top of the orientable, which means that there should be like a two-cycle in the geometry that is wrapped both by the branes and the orientable. On the other side, we had SU group, which arise from branes alone without orientable. So there should be some other two-cycle in the geometry that are wrapped only by the branes and at most intersect the orientable. So this shows that the fractional branes in the orientable should be in some sense misaligned. This should be the explanation, we believe, of supersymmetry breaking setup. Second, since we have a cascading gauge theory, it should be related. For this, we use our knowledge of Kleban-Strassler's and other construction. So it should imply that the metric warp factor should receive log corrections, and eventually we expect the singularity to be smooth deep down in the bulk. Again, the distinction between m odd and even just told us that we have to be really careful in selecting the charge of the orientable. Then now that we did this, we are wondering, maybe this is like a list of instructions that we could use to find other DSB, starting from the brane construction. This question, however, is not answered yet, but it's something that we would like to check out. Let me now conclude. I showed you that it's not difficult to find DSB models in brane construction. There are many of them. And actually, we expect to find more. In some of our papers, we also find another model that I didn't talk about for simplicity. Its name is the 3-2 model. Second, we saw that it is quite subtle to embed these models into large completion. In particular, it requires the singularity to be isolated. And lastly, we found a large inversion of the supersymmetry breaking models, which in principle opens the route to finding a dual warp throat solution. Thank you for your attention.
Thank you. Thank you, Antoine, for a very nice talk. Again, let's all use the clap emojis. We have some time for questions from the audience.
Yeah, please.
So if you have a question, you can just unmute yourself. So maybe while we wait, I can ask you something. So have you thought about the implications for the Swampland program? Can you comment a bit on this, like the non-SUSY DS conjecture?
So the first thing that I can say is that when people discovered this instability, the one that I spent time to explain, they actually formulated a Swampland conjecture. And indeed, we proved that with a theorem that it was well-founded, it would apply generally. So indeed, it connects well with the Swampland conjecture in this case. But then we found that we've isolated singularities with a sort of evading that. So what it means is that maybe there is an instability channel in the string theory, in the full string theory, but for some reason we could not see it in the gauge theory. So that would be definitely something to investigate on, but I cannot say much more. Then, yeah, it's really tempting to connect it, this result to the non-SUSY ADS conjecture, because in some sense we expect this warp throat to be at least to look locally like ADS. But the thing is that still the asymptotic is different. It would not really be ADS in this case, like for the conical is in the case. So it's not really easy to compare this result, I would say. But yeah, it's definitely something I would like to investigate on.
I see. I see. Thank you. Is there any other question?
Can I ask you one very technical question?
Sure.
If I understand correctly, what you're showing is that it is easy to engineer, or it is possible to engineer a toric singularity in which the gauge theory cannot satisfy the atom equation. Is it correct?
So here it's say the breaking arises dynamically.
Yeah,
so
exactly.
To strong
yeah.
dynamics and such. So in this kind of setup, we don't really solve the F-term equation because it's not the breaking that arises classically.
But then if you include the dynamical SUSY breaking term, then you can show, can you show that the F-term equation cannot be solved? Is it the reason why there is SUSY breaking, or there is a D-term, like, can you phrase it in terms of F-term SUSY breaking or the D-term SUSY breaking? But then you have the actual question that I was going to ask is that the confusion that I had is that in the gauge theory, when you decouple gravity, even though you can oftentimes show that due to the fact that F-term or the D-term cannot have a solution, if you're trying to lift them up to the gravity theory, due to the fact that F-term equation or some, the full potential now also receives some corrections from the Keller potential, is really difficult to show whether or not the SUSY is fully broken even in gravity lift. So is it possible to actually show that even in the gravity lift, the SUSY is broken due to the fact, despite the fact that it's going to be really tricky to compute the Keller potential?
So you mean when you say gravity lift, you mean that we include back gravity into the game?
Yeah, like compactify the Calabi-Yau.
Yeah, no, these would probably change completely the story. At this point, when I say that we have full stability, it was really at the non-compact level, when we can really decouple gravity. I don't expect these results to be true anymore when you compactify, but since the breaking was stable before compactification, probably it can give you more reliable metastability, like gain some control. But for sure, the main conclusion would change at this point because you change the rules of the game.
I see. Thanks a lot.
Thank you for your question.
Okay, great. So I think it's time we should wrap it up. So thanks again to both our amazing speakers.